Hello, Chem students. This is going to be another topic, Chapter 1 topic on atom shapes, hybridization, sigma and pi bonds, how to draw these, including 3D shapes. We're going to find that there's three shapes that we observe in organic, and it turns out biochemistry as well, and they're shown right here. These all should have been seen in your freshman chemistry, but we're going to go through them in a lot of detail, in case you don't remember. The three shapes we need are a tetrahedral shape, which looks like this. There'll be four single groups around a central atom, the carbon here, but we'll also see that with nitrogen and oxygen. And then we'll have a second shape. Oh, and the bond angles, if you remember back from freshman chem, were said to be about 109.5, but there's a little wiggle room in there, so they're not exactly 109 usually. Then we'll also have a shape that's called trigonal planar shape, and that'll be sort of a flat shape divided up into three equal wedges. So the bond angles are, perfectly 120, but they're never just perfect. So there'll be something a little different, but we're going to look at them as being 120. And then the last shape that we're going to have is when there's two groups around a central atom. We'll call that linear shape, linear carbons. That'll also be possible with nitrogen and oxygen. And the bond angles here will be 180 degrees. So we need something to explain these shapes from the atomic orbitals that we developed in our earlier topics. This particular molecule right here is called methylalene. It's a combination of all the shapes. So in the end, you have the trigonal planar, and in the middle, you have the linear, and in the middle here, Ca, you have trigonal planar, and then at the end you have tetrahedral. So those shapes are all within a single molecule. Every atom will have its particular shape. Now the way we're going to do this is called hybridization. So hybridization is when we mix things together, and we're going to mix the S, the 2S, with different amounts of P. So our first example is going to take a sort of an imaginary carbon, which I have here. And these are the atomic orbitals that we would, say, develop from freshman chemistry. Real carbon doesn't behave this way in molecules. But what we're going to propose is that one of the electrons is promoted up. And so that way we'll be able to make four bonds. And making four bonds, we'll be able to get the octet configuration, which is what the carbon wants to be. Now, when they're in this particular arrangement, we're going to take the S with one of the P's and mix them together. That'll be the hybridization, like hybrid roses, hybrid cattle, things like that. Now we're still going to have the two P's over here. We have two of them, two 2p orbitals, and they're going to behave as in a manner that forms pi bonds. So I have here sort of a pretend example to show how this results. The carbon 2s would be here looking something like this, and the carbon 2p would look something like this. In reality, they're both centered on the carbon, on the C. But we took them apart so we could look at them individually. And then we're going to add these together. And so when we add them together, you'll notice that I included the phase in this picture of the P. The similar phase will add together constructively and become a bigger lobe. And the lobe represents the electron density. And then we have the opposite phase. They will cancel out. And so you'll have the opposite phase, and that also represents electron density. Now, in the end, we're going to leave this off because it just makes the picture look a little messy. And so at our level, this is fine. Okay? We're mainly interested in where the bond is, and the bond will be on the side with the big orbital. Now this combination, since we use an S and a P, we call this an sp orbital. And you'll notice in the shape that I have here, it's pointing to the left. Now mathematically, what we're going to come down is mix them a different way in terms of our simplistic view. Instead of adding them, we're going to subtract them. So this time, when I subtract this, the phase signs will change. So I'll have one phase here that was on the right, now it's on the left, and this phase here. Now when I add these together, the similar phase will be on the right this time. So it looks very similar to what we have up above, but it's pointing 180 degrees in the opposite direction. Now it's pointing 180 degrees because the orbital we created it from is a p orbital, which is a linear shape right here, and that's 180 degrees apart for each of the lobes along that straight line. So I have another sp, we'll leave the little lobe off, and so we'll have two of these, right? Now remember, we still have the two p orbitals that are left over, so I have one in the vertical direction and one out in front and back. Okay, that's still a 2p. Now to actually put this into a molecule, I have to make a bond with all of these orbitals. An sp on the right, an sp on the left, a 2p up and down, and a 2p front and back. So the easiest way to do that would be to take another carbon that looks just like it. So you'll notice I overlap in the middle. The two sps, they overlap, and one electron in each makes a 2-electron bond. That's called a sigma bond. Remember, the sigma bond is always the first bond. Now on the other side I have an sp orbital, and just to make it as simple as possible, all we're going to do is bring up a hydrogen with one electron and overlap to make another sigma bond in the opposite direction. So you'll notice these are all in a straight line. The carbon, and the hydrogen. On the other side we're going to do exactly the same thing, and so that will continue the straight line to the other sp orbital here with this CH. And so that'll finish off all of the sigma bonds. Now in the vertical direction on this carbon, I'll have an overlap with the vertical direction on this carbon, and that'll be a pi bond. I'll also have an overlap in front and back, and that'll be a second pi bond. So even though I draw two lines, top and bottom, or front and back, that's just one bond. That's a pi bond. But you'll see I have two pi bonds here, so in fact, between these two carbons I have three bonds. I have the first bond, the sigma, and the second and the third, which are pi bonds. So with all of this, shape that we have here, this will go together to form what we call sp hybrid carbons, but we'll see this is for nitrogen and oxygen too. The shape will be linear. The bond angles around the sp carbon, so I'm just looking at a single atom, are 180 degrees, because that's the hybrid orbitals. The number of sigma bonds for this particular carbon will be 2, 1, 2 on either side. The number of pi bonds will be 2. Okay, we have a p orbital up and down, and we have a p orbital front and back. So this whole thing is a package. Okay, so we can tell any of the other features of this package from any of the given information. So if I know the bond angles are 180, I know it's linear, and I know it's sp hybridized. Now we're going to draw it a little more efficiently than trying to draw all these lobes and everything, which get to be kind of messy and hard to draw in a big molecule. So the way we're going to draw it is we'll just draw single lines for sigma bonds. So you'll see they're all in a straight line here because these carbons are both sp. And then I have a single line up and down, and a single line up and down, and then an overlap of those two lines. That's the pi bond. I'm going to draw two dots for the pi electrons. All right. And then in front and back we need to be a little bit of an artist here. And so we're going to show a heavy line when it's out in front, and we're going to show a dash line when it's in the back. Okay, anything in the plane will just be a simple line. So you notice this p orbital, whoops, sorry about that. This p orbital right here has a wedge and a heavy line and a dash, heavy line and a dash, and so they overlap. And then we draw the two electrons for the pi electrons, the pi bond. Okay, so this will be our picture for a triple bond. Now I actually made a model using my old models from the 1960s. They don't make these anymore, but they kind of correspond to exactly what we just did. There's a sigma bond in the middle. Here's the CH over here. Here's the CH over here. You'll see it's all in a straight line. And then I have up and down, and then the overlap on bottom and top. That's a pi bond. And then front and back, that's a pi bond. So there's our triple bond in between. The more modern models, which may not be as good, or maybe they are, show it a little bit differently. It comes as a single piece, and so it's all in a straight line. And so this is the sp on the outside on the right, sp on the outside on the left. And then the carbon is here, and they show these little plastic planes to be the pi bonds. So one's up and down, and one's front and back. Okay, these are the Darling models. And I drew the picture down here so that you could try and correlate what our picture looks like with what we see up here. So this is what you're going to have to draw. So you want to kind of practice this a fair amount until you get pretty good at drawing it and visualizing it. Now, as I said before, this works for carbon, which we have already shown. So this would be a simple molecule, carbon-carbon triple bond with an H on both sides. That would be called ethine, has a common name of acetylene. But if I come over here and put a nitrogen instead, okay, nitrogen only makes 3 bonds in a lone pair. That lone pair is going to be out on the other side where this H would be, so it's in an sp orbital. Because notice the second and third bonds here are pi bonds using p orbitals, and so I'd only have one hybrid in here for the sigma bond. Okay, and that would mean that this has to be an sp nitrogen, linear shape. So instead of putting an H out here, I'll put a lone pair, and instead of putting a carbon here, I'll write a nitrogen. And this would be hydrogen cyanide, okay, which is a molecule, a well-known molecule. And we could even do this with oxygen, but there's a little bit of a problem because oxygen really only wants to make 2 bonds. However, if we look at carbon monoxide doesn't have anything else but the carbon and the oxygen. So it turns out that this will work. We can get our octet if we make a triple bond between these two. But if we make a triple bond between these two, then that means we'd have a lone pair on the outside here and a lone pair on the left side over here. And for oxygen, that would be 1 bond too many, so we would write a plus charge, just like H3O plus if you remember in freshman chemistry. For carbon, we have 1 bond too few, but we still have the electrons, and so that's going to have a minus charge. And so overall, it'll be neutral, and that would be carbon monoxide gas. Okay, so even an oxygen can do this, but like I said, it's a little bit different for oxygen, and we have a formal charge. Now, if I come back and look at the hydrogen cyanide, there's a little thing we can do that's going to be kind of a challenge for you guys, and that is we can move the electrons around in the pi bonds. So what I'm going to do is I know nitrogen has a larger Zeffective and has a greater attraction for the electrons and has a higher electronegativity. So what I'm going to do is I'm going to arbitrarily move the electrons over and give them to the nitrogen. Now you can tell this isn't going to be great because I just broke a bond and I have an incomplete octet on the carbon. So this is not as good a resonance structure. These are called resonance structures when I do this. This is not as good a resonance structure, but it's a valid structure because I'm giving the electrons to the nitrogen, which is electronegative, more electronegative, and already partial negative anyway. So this kind of reinforces our generalized picture of what the nitrogen should look like. Now I don't do it the other way. I don't take the electrons and give it to carbon because carbon's not more electronegative. It's less electronegative. And so that's not going to be nearly as good a resonance contributor. So I did it with the 3D structure here, but we could also do that with the 2D structure. So I just move the electrons over. That's what the little arrow shows us. It points to where the electrons are going, and it starts to where the electrons are coming from. And so again, I would get something that looks like this, and I would write the formal charge minus on the nitrogen plus on the carbon. Okay. Now I could do this with the oxygen, with the carbon monoxide up here. So when I do that, you almost look at it and think, well, maybe that makes more sense because the oxygen really doesn't want 3 bonds. So if I move it over, the oxygen would have the right number of bonds. Okay, it would have 2, but you'll notice I stole the electrons from the carbon. So the carbon has an incomplete octet. So as far as the carbon's concerned, this is not particularly good, even though it goes to a neutral formal charge. I could actually do it one more time with the electrons in the other pi bond, and I'd end up with the oxygen having a minus charge, which seems reasonable since oxygen is more electronegative. And carbon would have a plus charge, but now really only 4 electrons around the carbon. So that's going to be not real good. Now this has actually been calculated theoretically in a paper, and the paper that I read attributed the first structure with full octets as being the best one with 50% contributor. And the one with no formal charge but 1 fewer bond and incomplete octet was considered to be a 40% contributor. And then the last one down here was considered to be the weakest contributor, 10%. But you'll notice they all contribute somewhat. Okay, so we're going to have to become more familiar with these resonance ideas. Okay, we're going to go to our second hybridization, which is sp2. So we go back to our original picture and promote this electron. So that cost us some energy, but we gain some energy because they're not in the same orbital, so they're not repelling each other anymore. And then now it allows us to make 4 bonds. Now this time we're going to mix the s with 2 of the p's. Okay, so those will be our hybrid orbitals. We'll make 3 new orbitals, we'll call them sp2. But we still have one 2p orbital left over, and that will become a pi bond. Okay, so let's see how this looks on an atom. I took the 2s out just to look at it, and now notice we have two 2p orbitals, and that's going to define a plane. So our new hybrids are all going to be in the shape of a plane. I put the s back in, and then I overlap where there's the common phase. Mathematically, this is a little more complicated than we did with the sp. So I'm only going to show one of them, just to show I have like a common phase here. That'll be a bigger lobe. And then a little phase in the back that's going to cancel. We're going to forget that. We're going to drop that out. Now I can do this three ways. And so I've only shown one way here. And if they're all in the plane and they're all equal to each other, we should be able to sort of predict what the angles would be. So if I took a plane, a circle and a plane, and divided it into three equal wedges, I would have 120-degree bond angles. And that's what we're going to say the bond angles are for these sp hybrid orbitals. If I come over and draw the carbon and put in, say, these lobes for the p orbital with the phase and everything, that would work, but it's a little more complicated. So the way we're going to do it to make it a little simpler is this: we're just going to write simple straight line up and down for the p orbital. Now around the outside, I have the three different sp2 orbitals, and they're pointing in directions that put 120 degrees between each of them. You'll notice I have one in the plane of the paper, in this case pointing right, and then I have a dash and a wedge, because I'm looking at it side on. All right? Now to make a molecule, I'm going to need something that overlaps with all of those. So like we did before, we'll take a similar hybridized atom, in case another sp2 combined with an sp2, and we'll overlap in the middle with the hybrid orbitals. That'll be a sigma bond, and that's our first bond. Okay. The other hybrid orbitals, we'll finish those off with just a simple hydrogen to be as simple as possible. And that would be a sigma bond as well. So one will be in the back and one will be in the front. You'll notice this carbon is pointing towards the right. This carbon here is pointing towards the left so that they can overlap together. But it still has a lobe in the back, sp2 orbital with a hydrogen, and an orbital coming out in the front, sp2 orbital with a hydrogen. And so those will all be sigma bonds. Now the p orbital that's left over, up and down here, will overlap with the p orbital on the other carbon up and down here. And so even though there's two lines, that's just one bond. That's our pi bond. And the way we'll draw it is a little more simple, because we'll just use single lines for those p orbitals and then a line to show the overlap. And then include two dots for the electrons. Now again, we have a package deal over here for the sp2 hybridized carbon. The carbon shape will be trigonal planar, but remember this is the same shape we'll see for nitrogen and oxygen. So they will also be trigonal planar. Hybridization will be sp2. The bond angles will be 120 degrees. And in the case of carbon, we're going to have 1, 2, 3 sigma bonds, and then we have one pi bond up here. Since it's carbon, we don't have any lone pairs. With nitrogen and oxygen, we'll have some lone pairs, but everything else will be sort of the same. So remember, this is the package deal. If you say sp2, you're saying trigonal planar, you're saying 120 degree bond angles. So a simple little molecule for us will look something like this. There's actually a lot of ways to draw this. I've drawn it in the plane, the pi bond in the plane, but we can draw it with the pi bond coming out, and we can draw it with the pi bond going back. So this is one of our most versatile hybridizations in terms of ways to draw it. If we look at the whole molecule and counted up all the sigma bonds, we'd have 1, 2, 3, 4, 5 sigma bonds and one pi bond, and no lone pairs. But remember, if you look at just a single carbon atom, you can only have 4 bonds. So a single carbon atom, come back up here, we would have 3 sigma bonds and one pi bond. So again, I tried to make a model with my old models. I don't think you can find these models anymore. But you can see it kind of fits perfectly with the way we are proposing it in our slides here. Okay, it shows the two parallel p orbitals and a top and bottom overlap. So this guy in the middle is the first bond, that's the sigma bond, overlap of the hybrid orbitals. And this is the Darling models. They don't make a distinction between the two different bonds in the middle. They just draw two lines to show that there's a double bond. You would have to know that one of these is a sigma and one of these is a pi. So this is the way we're going to draw it. You'll notice it looks pretty similar to my model up here. Tiny bit different here, but all they're trying to show here is that there's a double bond, and you have to know what the arrangements are. Now we can do this with nitrogen. So again, I did this with nitrogen, but notice what happens. Nitrogen only makes 3 bonds. I got the sigma bond and the pi bond and a sigma bond with H. And then the fourth one is a lone pair. So that again, that's a hybrid hybrid orbital, sp2. And as before, I could move the electrons over to the nitrogen because it's more electronegative. I don't change the shape of any atom. I don't change the orbitals at all. I just change where the electrons are. But when I do that, I stole the electrons from carbon, so it becomes plus, and I gave the extra electrons to nitrogen, so it becomes minus formal charge. This is not as good a resonance structure, but it is still a valid resonance structure. It's useful in certain situations to look at it this way. I could do this in a two-dimensional form. I could start with the carbon-nitrogen double bond, push the electrons. Notice the arrow again. The arrow starts where the electrons are coming from. The arrow points to where the electrons are going. And then I have the minus charge. If I had this resonance structure first, I could do exactly the backwards way. I could push the electrons back in, so they're shared in between, and they started at the lone pair here. So I could do the resonance back and forth, but notice the arrows that I show only go towards the direction of the next structure. Okay, I don't have any arrows here because there's not a following structure to show. Now oxygen will do this too. So oxygen can make a double bond. So here's a sigma, and here's the pi, top and bottom. And notice now oxygen only needed 2 bonds, so what's left over are lone pairs in hybrid orbitals, sp2 hybrid orbitals. The carbon over here, I just finished off with a simple 2 hydrogens. I can move the electrons to the oxygen. This should be even better because oxygen is more electronegative. And so again, the oxygen gets some extra electrons and has a minus charge. We stole those electrons from carbon, but I still have the p orbital there, so I still show that, but it's a plus charge. So this is not as good as the first structure, but it's still a valid structure. We could show this in 2 dimensions just by moving the electrons to the oxygen. Now we have 3 lone pairs, we have a minus charge. Carbon lost its pi bond, so there's no second bond here, and it has a plus charge. If I started with this structure, I could bring these electrons in and make a double bond. So this would be a better structure, but this would be an allowable structure, and if I started here, I could show how that forms. Now, because we have 2 bonds, we could even show this with fluorine. Now, fluorine normally only makes 1 bond, but if I had a pi bond, a second bond right here, this would work for fluorine if we put a positive formal charge. Okay, so this will be what we call a resonance structure. If I take those electrons and move them to the fluorine, okay, now the fluorine is perfectly happy. It's got 3 lone pairs and a single bond. Now the carbon was sharing those electrons to complete its octet, but we stole those electrons back. And of course, fluorine, this is going to be the best for fluorine, but now the carbon has a plus charge. So this is definitely a valid resonance structure, as is this one. And we could show that with the 2D structures just by taking the electrons from the double bond, pushing them to the fluorine. So now I have 3 lone pairs. One thing that's hard to see here is the lone pairs are not all the same. Okay, notice in this lone pair I'm drawing it as if it's in a p orbital, 2p orbital. And these 2 lone pairs I'm drawing them as if they're in sp2 hybrid orbitals. But we don't see any of that over here. So that's sort of hard to see, invisible. I could take this structure and I could push those electrons back in and make the double bond. And carbon's really going to like that, okay, because now it has a full octet. Of course, fluorine has a plus charge, and fluorine doesn't really like to share its electrons. Now, I'm just showing you here all the ways we can draw this double bond. Okay, this is the way we've been drawing it, where the pi bond's in the plane. But notice the pi bond could come out of the plane. If I started with this carbon here, I'd have a wedge. And if I put a carbon here, I'd come out again, I have another wedge. So that would be if I started here. The same picture over here, if I started with this carbon, would be a dash. So you'll see this carbon in the middle could be a dash or a wedge, depending on which carbon atom you drew first. Here I drew the back carbon first. Here I drew the first carbon first. But the other bonds are all the same. This is a wedge, this is a wedge. This is a line pointing to the right, this is a line pointing to the right. A line pointing to the left, a line pointing to the left. And this is a dash back, a dash back. So it's only the middle bond right here that's ambiguous. So that would be coming out, say, from this carbon. Or, say, the pi bond's more towards the right, instead of actually going back towards the right. So in this case, it looks like I drew this carbon first because I have the wedge coming out. And so if I came over here and I drew this carbon first, I'd have the dash going back. So you can see either way, that's going to be a connection between these two, but it will be ambiguous. The other bonds are the same: wedge, wedge, line to the left, line to the left, line to the right, line to the right, dash, dash. Okay, so you should be able to draw any of these, visualize any of these, and then you can handle almost any situation for sp2 atoms. I'm showing carbons here, but they could be nitrogen, they could be oxygen. There's so many possibilities here. Okay, I drew some of them down here. So I just drew XY, because X could be both carbons, carbon and nitrogen, carbon and oxygen, nitrogen and nitrogen, nitrogen and oxygen, oxygen and oxygen. And I could do some of these with positive formal charge. Okay, so that's another variation. Now, all of these guys, everything that I've shown you on this page is one of these two forms here. I either have the central atom with the bond in the page going to the right, and then a dash and a wedge on the other side, or I have the bond in the page pointing to the left with the dash and the wedge on the other side. Okay, if you look at every single atom here, it's going to be one of these two possibilities. So try and visualize that, try and get that in your head in terms of your practice with drawing this, and you should do pretty well. Okay, our last way of hybridizing, and this is really, it's going to cover everything we talk about: carbon, nitrogen, oxygen, fluorine, everything on all the shapes, just 3 hybridizations. This time we're going to promote that electron, so we have 4 unpaired electrons, so we can make 4 bonds. We're going to mix them all together this time. So since it's an S and 3 of the P's, we're going to call these sp3 hybridized. Since I have 4 atomic orbitals here, we're going to end up with 4 orbitals over here, and they will all be equivalent to each other. Okay? So mathematically, this is a lot more complicated to try and visualize, and we won't try and visualize every single one. So I have all 3 of the p orbitals. You'll notice we fill up 3 dimensions now. So our new orbitals that we're going to make are going to fill up 3 dimensions. So I'm going to take the S and put it back in the middle. You'll notice now I have all the similar phase in one octant. Okay, not a quadrant, an octant. And so that'll be a big lobe out here and a little lobe back that we're going to forget about. So we're going to cancel that out. But I'll be able to do this 4 ways. Now, I don't think any of us have the intuition for how 4 orbitals in 3-dimensional space would arrange themselves to be as far apart as possible. But you know from freshman chemistry that the bond angles are going to be 109. So I've shown the carbon here with all of its electrons, 1 in each orbital, each of them being a hybrid orbital. Since I don't have any p orbitals, we're not going to have any pi bonds in this case. So this is the first one where I could just bring up a hydrogen at the end of each of those orbitals and finish off the molecule. And that would be CH4. CH4 is methane, so a very common molecule these days. That's sort of natural gas that they frack out of the ground a lot. And so we're not going to draw with all these lobes. First off, you notice how they kind of overlap each other. It's kind of hard to see where everything is. So we're going to simplify it down to lines. Remember, lines that are simple are in the plane of the page or the paper, and then the wedge is in front and the dash is in back. So this will be what we call a tetrahedral carbon, but we will also have tetrahedral nitrogen and tetrahedral oxygen. In terms of our course, they will all be tetrahedra. Now, I could connect 2 carbons together, as in all of our other cases where we needed the pi bond. So in this case, I connected these 2 guys, and I drew them in a certain arrangement where the bonds in the page, the simple lines are going down, up, down, sort of a zigzag shape. We'll study this a little more later on. And that allows rotation around this bond right here, so we could draw it different ways. So we'll have a whole topic on that. I think it's chapter 5, where we look at conformations, or rotations around single bonds. So this is a package deal over here. Carbon shape will be tetrahedral, but remember nitrogen, oxygen, fluorine. Hybridization will be sp3. Bond angles are 109. In freshman chemistry, you might have learned like 109.5, but really they vary a little bit. Number of sigma bonds is 4, no pi bonds. Since it's carbon, no lone pairs. So these all go together. So you should be able to write write from one of them, you should be able to write all of them. Again, I made some models up. These are my old models. And then the Darling models look kind of the same on the tetrahedral guys. Okay, so this is a carbon, and then the white guys out here are hydrogen. This would be ethane. This would be ethane. And then this is the way we would draw it. But there's many ways to draw it. Okay, with the dashes and wedges pointing in slightly different places. If I counted up all the sigma bonds in this molecule, I'd have 1, 2, 3, 4, 5, 6, 7. 7 total, no pi bonds, no lone pairs. But if I look at just one carbon, I have 1, 2, 3, 4. Because remember, carbon only makes 4 bonds. So I'd have 4 sigma bonds. So now what we're going to do is we're going to try and draw representations of some of these other atoms with nitrogen and oxygen. So you'll notice how I wrote this formula. This is a condensed line formula. And so you'll have to be able to interpret how these atoms are connected by the way it's drawn. So I show 3 hydrogens on this carbon, and I show 2 hydrogens on this nitrogen. You would have to remember that nitrogen also has a lone pair, and put that in. Excuse me. Now I could also have written the CH3, so I put the H's between the carbon and the nitrogen. You know that they can't be bonded all together and to the carbon and nitrogen. They only make one bond, so they have to be gathered around the carbon. So these are 2 ways of drawing it that you might see, but you have to interpret what the proper way is. Okay, and we could do the same thing with oxygen, but now oxygen only makes 2 bonds, so I don't have, over here I have NH2, I don't have OH2 here, I have an OH. Okay, and then with fluorine it could also be the same way. Put the H's in between or put the H's on the left. You know they have to belong to the carbon. Fluorine only makes 1 bond, and that would have to be with the carbon. Okay, so let's see how this looks. So here's the picture we drew before. That's ethane. It shows all of the sigma bonds with the hydrogens and carbon, and the carbon and carbon. But now with the nitrogen, picture changed a little bit. I have an N instead of a C. I have a lone pair instead of that CH. But otherwise, the orbitals are all in the same spot. But this time I only have 6, 1, 2, 3, 4, 5, 6 sigma bonds, no pi bonds, and 1 lone pair. Okay, if I come over to the oxygen, again the picture looks pretty similar. Carbon looks exactly the same, but the oxygen now has only 2 bonds, so I have one of the bonds back, but I could have drawn it out in front, and I could have drawn it down here, but wherever I draw it, the other 2 have to be lone pairs. Okay, so that would be what we call methanol. This would be methylamine. And then the fluorine would work too, but now all 3 of these would be lone pairs. So the fluorine does not have any extra atoms because it only makes 1 bond. Now the Zeffective, remember, carbon is +4, nitrogen is +5, oxygen is +6, fluorine is +7. So each of these atoms, the carbon, the nitrogen, the oxygen, and the fluorine, will hold the electrons tighter and tighter and tighter. So down here, fluorine has the greatest attraction for the electrons. Okay, that's going to pull the electrons away from the carbon a little bit, but it can't quite steal them all the way. And so the fluorine will be a partial negative, and the carbon will be a partial positive, even though we don't actually show the formal charge. Okay, so you'll notice there's no resonance structures this time, because resonance in our course only occurs in pi bonds and 2p orbitals. Okay, so if we don't have any 2p orbitals, we don't have any pi bonds, we don't have any resonance. Generally, if you have a whole bunch of these guys in a row, we want to put them in what I call a zigzag shape. Okay, that way we're just looking at them all side on in the paper, and it's kind of easier. If you tried to draw this coming out of the page or going in back of the page, you'd have to be a pretty good artist. But if you just draw it in the page, you don't have to be so great of an artist. So notice the fluorine I have going up and then down, up, down, up, down, up, down. So that's the way we'll draw it. And then off of each atom, I have a wedge and a dash, a wedge and a dash, a wedge and a dash. Now once you draw the wedge and dash on the top a certain way, all the other ones will be just like it. But there's 2 different perspectives. So in this case, we're looking at it from the right side. So the wedges and dashes could look a little different if we looked at it from the left side. And then wherever the dash is here, the wedge will be in that same general direction, because it's like 180 degrees opposite. So it would be coming out parallel to this one here. And then the dash here would be parallel to the wedge here. And once you draw one of these, it's going to be the same all the way down the line. Okay? And you'll notice when I'm at fluorine, I make all of these lone pairs. Then I have 4 bonds on the carbon, 4 bonds on the carbon. Then oxygen, I have 2 lone pairs. coming out and going back. 4 bonds on the carbon, 4 bonds on the carbon. Then when I get to the nitrogen, one of these guys will be a lone pair. Doesn't make any difference which one you choose. So now these are our shapes, okay? And the way we label them is different than the way you label them in freshman chemistry. We're going to call all of these guys, all of them, tetrahedron. But in freshman chemistry, you probably called this a tetrahedron, and you probably called this pyramidal, and you probably called the water molecule bent, and you probably called a molecule like this HF, HCl, HBr, linear. Okay. Now, in terms of tetrahedron, we said the angle is 109.5. For methane, that's going to be exactly what it is. For ammonia, it turns out that the lone pair here is pulled in closer to the nitrogen because there's nothing on the other side pulling it away. And when the electrons come in a little bit closer to the nitrogen, it pushes these electrons down because they repel each other. So the bond angle shrinks a little bit. Now, as far as we're concerned in our course, we're going to say it's 109. We're going to say this is 109. But in freshman chemistry, you probably learned this is a little less than 109. If we look at oxygen, it has 2 lone pairs, no atom on the other side, so it's going to pull these electrons in closer and tighter, and that's going to repel these electrons away, and so they will be pushed a little bit closer because there's a hydrogen out here kind of pulling on them away from the oxygen. And so the bond angle shrinks a little bit more, so that's going to be like 104.5. We're just going to say it's 109. All right. Now fluorine really doesn't have any bond angles because there's just the H and the F. That would be linear. But we're going to look at the orbitals as just being like, say, the orbitals over here with methane. And so we'll still consider this to be like a tetrahedron with 109-degree bond angles. So that's not exactly correct, but for our course that'll work. Now this is why I don't worry about the little 0.5 or the 7.8 or whatever it is. Because if I take another atom, say I put a methyl group down here, a methyl group's kind of a big atom compared to just a little hydrogen up here. It's got its own bonds and extra hydrogens, so that's going to repel the other groups around here. And if I had another methyl over here, they would repel each other more because they're larger groups, and so that might push them out away from each other, spread them out a little bit, and so the angle would be bigger than 109. Let's see. Okay, so it turns out that the angle between the 2 methyls is 112. So what does that 109 mean? Okay, you can see the sp3 hybridization has a variable range of bond angles. And when these spread out a little bit, it pushes these 2 a little bit closer. So these now are about 107. So we're still going to call this 109. Okay, we're not going to make any big distinctions about this. But this is more real. This is more related to what's really there than what we do. Okay, now the lone pair is still going to pull in close a little bit, but now if I put a methyl at each of these spots, they're going to push back a little because they're big and they repel each other. So I'm expecting the bond angles would increase. Say here it's 107.8. Now it's 110.9. So these have increased, okay, because there's repulsion between them. And over on the oxygen, where we had 104.5, if we put methyls there, so we have dimethyl ether, we expect those to push out a little bit. And they do. So now it's 110, whereas it was 104 up here. All right. So the CXC, all those angles got bigger. Okay, and that's because these are larger groups that repel each other. This is a little more complicated. I tried to put in a little bit of everything. So here's a tetrahedral carbon, 109-degree bond angles. Here's a trigonal planar, bonded to a trigonal planar. I must have drawn this one first because I have a dash here. But the wedge has to be a wedge, and the dash has to be a dash here. So you can see how this looks. And then I come over here, and this is linear. That would be this part right here. Okay. And then I put in another tetrahedral carbon on the other end. And then I built it with my old-fashioned models from the 1960s. So I hope that you can see the triple bond and the double bond and so forth. Okay, I'm going to be expecting you to draw these kinds of structures. So this structure right here should be something that you're able to draw with a little practice. If we put in the hybridizations, the bond angles, the shapes, and so forth. I see I made a little mistake here. I didn't put in the pi bonds and the lone pairs. There are no lone pairs, so that's okay. But the trigonal planar guys should be 3 sigma bonds and 1 lone pair, 3 sigma bonds and 1 lone pair. Linear should be 2 sigma bonds and 2 lone pairs. 2 pi bonds, 2 sigma bonds and 2 pi bonds. And tetrahedrons 4 sigma bonds. So that's a mistake. Now, how are you going to figure out, when you look at an atom, how are you going to figure out what its hybridization is? And the way I'm going to suggest you do that is you look at the atoms, say this carbon right here, and you look for a second and or third bond. I do not see any second bond here. Okay, so this has no pi bond. If it has no pi bond, then you're going to mix all of the available orbitals, which is the 2s and the 3 2p's. You're going to mix them all together, and that will make this sp3. And if that's sp3, then it's going to be tetrahedral. It's going to have 109-degree bond angles. If it's carbon, it's going to have 4 bonds. Okay, now let's take a look at this one. This one I see there's a second bond here, so I can see that there's a pi bond. The pi bond uses a p orbital, so I'm going to come over here and I'm going to cross that one out. And then I mix whatever is left over. So I mix the s and the 2p, so that's going to be sp2. And if I say that's sp2, then I'm saying it's trigonal planar, and I'm saying the bond angles are 120. Okay, so we look for the pi bonds to decide. If I come down here and look at this one, I see there's a triple bond between these two. So the second bond and the third bond are pi bonds, and those use p orbitals. So I'm going to come over here, I'm going to cross out these 2 p orbitals because they're making pi bonds, and this is what I have left over. I have an s and a p, so these will be sp hybrid carbons. So if it's sp hybrid, then it's going to have 2 sigma bonds, 2 pi bonds. It's going to be linear. The bond angles are going to be 180. So remember, all of that goes together for carbon here. This has different possibilities. On the end, I have 1 pi bond, so that's sp2. The middle carbon here has 2 pi bonds, one pointing to the left, one pointing to the right. So that's going to be linear, sp. And the carbon on the right only has 1 pi bond, so that's going to be sp2. But because the p orbitals in the middle are perpendicular, the planes of this carbon and the planes of this carbon are going to be perpendicular to each other too. Okay, because the p orbitals are in the middle here are perpendicular. So that carbon in the middle is going to lose 2 p orbitals. It's going to be sp. So that'll be a linear shape. So how do you know what the hybridization is? Okay, you count the number of pi bonds that an atom has. Say in this case 1, and in this case 2. Okay, and those are using 2 p orbitals. And then you mix the 2s with however many 2 p orbitals are left over. So in this case, there would be 1 2 p orbital left over. There would be 2 p orbitals left over, so this would be sp2. But in this case, there would only be 1 p orbital left over, so this would be sp. Now, I drew out structures with all the carbons and hydrogens this way. This one right here, I actually timed myself. It took me 45 seconds. So we don't really like to draw structures like this because it's so time-consuming, takes up so much space. So we have kind of a shorthand way of drawing it. But, of course, that puts a burden on you to interpret and draw for other people. It's going to look something like this. So this is called a bond line formula. And what we do is we leave out all the carbons and we leave out all the hydrogens. And all we do is draw lines. Now, if there's a nitrogen and an oxygen and a fluorine, we do draw those in. Okay? But in terms of the carbons and hydrogens, we leave those out. So if you look here, here's a triple bond. Okay? So when I come down here, I'm going to draw that triple bond. But at the end of the line, right here, there's an H that I leave out. And I don't draw the carbon. I have to recognize the number of H's here as 1 by looking at the bonds that I see. I see 1, 2, 3. But I know carbon makes 4 bonds, so the missing bond must be the hydrogen. If I look on this side, I see 1, 2, 3, 4 bonds. There is no hydrogen because I see all 4 bonds. But this must be linear, sp. If I look here, I only see 2 bonds, so there must be 2 hydrogens missing here. They must be hydrogens up here. If I look over here, I only see 2 bonds. There must be a CH2 here, hydrogens over here, and they're all single bonds, so these guys must be sp3 carbons. If I look over here, I see a bend here. I see a second bond. This is a pi bond. So this must be trigonal planar, sp2. I see a bond over here because these are carbons, but no carbon written. There must be another hydrogen up here that's not shown, okay? And if I come over here, this is also sp2, and there must be a hydrogen that's down here, just so that the shape is 120-degree bond angles. If I look over here, I see 1, 2, 3, 4. I see 4 bonds, so there is no hydrogen, but this must be sp2. If I come down here, I have to put a little dot, otherwise it would look like a super duper long pi bond. So this just shows there's a break there. And I have a second bond here and a second bond here, so this must be sp, linear shape. When I come down here, I only see 2 bonds, so there must be 2 hydrogens missing. But because of the pi bond, the second bond, that must be trigonal planar. There must just be a CH here, a CH2 here. This is a carbon with no hydrogens, but it's tetrahedral. This is the carbon here. It's just the end of the line. There must be a carbon there, but I don't see any hydrogens, so this must be a CH3. This must be a CH3, so those are tetrahedron. Now, this one, when I drew it, I timed myself. It took me 11 seconds. So if I look up here, and I look down here, I drew this one 4 times faster than this one. And so that's why we draw stuff like this. It's just a lot easier. But, as I said, it puts a bigger burden on you. You have to be able to interpret what do all these lines mean. So you got to think about it, practice it a little bit. You'll be able to get it. Okay, well, I actually went in and I did it all for you here. Okay. Now, I just sort of summarized all of our atoms right here, if they're neutral. We can do positives and negatives on all of our different atoms, but then those are less stable. We'll study that later. But for the neutral guys, carbon can make 4 bonds. All right, it can make them all single, or it could have 1 pi bond and 3 sigma bonds, or it could have 2 pi bonds and 2 sigma bonds, but carbon can do it 2 ways. So you could put pi bond on the right, pi bond on the left. Okay, but carbon likes to have 4 bonds, no lone pairs. Zeffective is +4, electronegativity is 2.5. So carbon's kind of like our reference point. And if you look at nitrogen, oxygen, fluorine, they're all more electronegative. So if they bond to carbon, they're going to pull electrons to themselves away from the carbon to put in some polarity. So nitrogen can make 4 groups. One of them has to be a lone pair, all single groups. That would be sp3. Nitrogen could have a double bond, so that would be sp2. The lone pair would have to be sp2 hybrid orbital. Nitrogen can have 2 pi bonds, that would be linear, and then the lone pair would be an sp hybrid orbital. We can't really make 4 bonds with nitrogen if it's neutral. We can make 4 bonds if we have a positive formal charge. So now notice the number of bonds for nitrogen. It's 3, and lone pairs is 1. Formal Z-effective is larger, +5, so it has a greater attraction for electrons. If we go to oxygen, we can only make 2 bonds. So those could be single bonds, and then the lone pairs would be single groups. So that would be sp3 for oxygen. But we could have a pi bond, second bond, and then the lone pairs would be in sp2 orbitals. We can't make 3 bonds if it's neutral. We could make 3 bonds if it's positive charge. Remember the carbon monoxide. And also remember in freshman chemistry, H3O+, hydronium ion. Okay, so oxygen wants to make 2 bonds, wants to have 2 lone pairs. Notice the Z-effective went up to +6, and its electronegativity increased. So Z-effective is higher, greater attraction for electrons. If we go to fluorine, we can only do it one way because fluorine only needs 1 electron to complete its octet. So we only have single bonds. So we would say this fluorine is sp3 hybridized. If we make 2 bonds, we can do it if it's going to be neutral. There is a way, remember we drew that earlier, if I overlap and make a resonance structure. But then we have to put a plus charge on the fluorine. So for neutral fluorine, we want 1 bond and 3 lone pairs. Has the highest Z-effective of the atoms we talked about. And then hydrogen doesn't have, all it has is s orbital, 1 s orbital. So no hybrid orbitals. It always makes 1 bond. There's no lone pairs, no pi bonds. Okay, so you don't want to ever draw 2 bonds with hydrogen and any other atom. Okay, that's not going to work. So up here in all these lines, our symbolism is that's 2 electron bond. Could be sigma, could be pi. Notice these 2 lines look the same, but we know one of them is a sigma and one of them is a pi. So here's a molecule you can think about. Okay, I have the answer on the next slide. I won't go through every single answer here, but we could ask ourselves, for example, what's the hybridization? SP, SP2, SP3, or no correct answer. So if I looked at, say, something like this nitrogen, I don't see any pi bonds, so I'd say it must be sp3. Now notice I only see 3 lines. There's something missing. I must have a lone pair that I haven't drawn in. So that's something I could do. Okay. And then I can answer questions like, what's the hybridization? What's the bond angles? What's the shape? What's the number of sigma bonds? What's the number of pi bonds? What's the number of lone pairs? What's the number of hydrogens? Because remember, we're not drawing in the hydrogens. We're using the bond line formula here. This is highly condensed, highly compact. So there's a lot of symbolic information here. And when you're a beginner, that's a little bit hard to see. Now notice we do write an H if it's on a hetero atom. Hetero means different. And so oxygen is different than carbon. And nitrogen is different than carbon. So if I have an oxygen with an H, I'm going to put the H in there. I'm not just going to write an O by itself. And if I have a nitrogen with an H, I'm going to put the H in there. And then I'd even do it on, this is called an aldehyde group. This is one group where we could write in the H. Most people do, but not everybody does. Okay. So this is something you can practice with. And like I said on the next slide, you have all the answers here so that you can double check yourself. I don't have any of the lone pairs here, but I drew the lone pairs over here so that you can see that. So I assume that you could take your time on this and kind of go through and do it. I won't look at every one because I've talked long enough on this. Okay. So that brings us to the end of another little topic on Chapter 1. I'll be doing some other topics as well.